So let me invite everybody for the first part today. Our speaker will be Śpiewak from IMPAN, and he will be speaking about prediction of dynamical systems from time delay measurement.
Okay, thank you very much. Thank you for an invitation to give this talk, especially that it will not be on complex dynamics. It will be on dynamical systems in the broad sense, though, so it kind of is related fields, I hope. All the new results that I will present today come from a collaboration with Krzysztof Barański and Yonatan Gutman. And this is a project in which we deal with the so-called time delay embeddings of dynamical systems and the so-called Takens theorems, which tell you something about this time delay embeddings. The general question or the general framework that one studies in this context is the following. Consider that we have a dynamical system, some maybe discrete time dynamical system, so just a transformation which we iterate, but we don't have access to the actual states of the system in consecutive time units. So there is a system, but we don't see how it evolves. What we see instead are values of measurements performed by some observable. So there is an observable on the system, maybe some parameter which we can measure, and what we see as time goes by are the values of this observable along an orbit of the system. And now the question is, to what extent, in what sense, the original dynamics can be reconstructed or modeled from this partial information that you gather via an observable. And in the classical settings, there is a family of Takens theorems, which originated from the work of Takens in the 80s, which give you conditions under which you can indeed reconstruct the dynamics, maybe up to some sort of isomorphism from these observations. And this is an example of a, mathematical, purely theoretical result, which made quite a career in applications. So this is something that is indeed invoked in natural science as a justification for validity of certain methods or algorithms to rebuild your dynamics from observations. And what we do is we, in some sense, study this theory from a new perspective. So let me begin with being a little bit more precise on what we mean by time delay embeddings and what Takens theorems say. But this still will not be rigorous. This will be sort of a general discussion, which then the details can be filled in several categories, depending on what we are interested in. So by T, I will denote the dynamics, which acts on the set X. And H will denote observables. And for a moment, an observable is just a function from X to the real line. Very soon, we will start imposing regularity conditions on the dynamics and the observable and some conditions on the structure of the set X. But this first slide is general, so I don't do it just yet. Soon, everything will be Lipschitz and X will be a compact subset of Euclidean space. And now, sort of general question that one might ask is the following. So the main object that we are interested in is the so-called delay coordinate map with the number of measurements k. K is a natural number, and this is a map defined on the phase space of the system, which I denote by phi with indices t and h, and it just assigns to an initial state of the system a vector of length k of values of the observable h along the first k iterates of the point X, okay? And now one particular question that one might ask is under what conditions, under what assumptions this map turns out to be injective for some k and typical in your choice of class observable H. So whenever this map is injective, this means, that there is a one-to-one correspondence between the states of the system and this measurement vectors. So at least in principle, if you can, using the observable, you can build a faithful model of your dynamics in RK, just knowing the values of the observable. This is somehow the ideology. And now we ask for this to happen for a typical observable. For us, this will be a typical Lipschitz observable very soon. Note that we cannot hope for this to hold for just any observable, right? If we take a constant observable, then we lose all the information. Or maybe if it's constant on a too large part of the space, then we lose too much information. But it is reasonable to ask for this to hold for a typical observable. And now what I mean by typical, again, depends on the category in which you work. So what is given here is a sort of a meta statement of several Takens type deterministic theorems. So this is not an actual theorem, but this is sort of a common essence of several of them. And they go as follows. So first of all, what they do is they give sufficient conditions for this property to hold. So for phi to be injective for a typical observable. And what are these assumptions? Probably the most important one is the bound on the number of measurements. As long as k is greater than twice the dimension of the set x, we are in business. And now again, what does dimension mean? This depends on the category. But this is somehow the threshold, and it goes in line, if you are familiar with those, with non-dynamical embedding theorems, like Whitney theorem or Menger-Nebeling theorem, stuff like this. We know that, well, in general, if you have set of dimension x, this is the dimension of the Euclidean space which you need to take in order to have a guarantee that you can embed into this space. So this is the most important assumption, but there are some additional assumptions about the dynamics. So the dynamics has to be injected. If the dynamics itself is not injective, then it might glue points too early and you won't be able to distinguish them by observable. And there also cannot be too many periodic points. And what I mean by this, I will make it more formal soon, but it is easy to see that indeed periodic points of low period are obstructions for this sort of results to hold, because, for example, if the whole space is fixed, then this is just a constant vector. So phi is injective if and only if h is injective. But h is injective. This means that actually your set x embeds into the real line, which we cannot hope for if the set x was to be, right? So there cannot be too many periodic points. And under these assumptions, in several categories, people have proved that for typical observable, this map phi will be injective. The most famous result is one by Takens. This is in the smooth category. So this is for C2 diffeomorphisms of C2 compact manifold. He doesn't have this assumption on periodic points, but his result is only for generic dynamics. So somehow the assumption is hidden in the genericity of the dynamics.
Kukas-Meyer.
Exactly. Now, maybe the second one, most famous result is by Sauer, Yorke, and Kasdagli in a paper called Embeddology, where they extended this to arbitrary compact subsets of Euclidean spaces in the Lipschitz category. So everything is Lipschitz, and the notion of dimension that they use is the upper box counting dimension of a compact set. And as I already mentioned, this results, they are indeed being invoked in applications as a justification for building this model of an unknown dynamics from observations, and you can find papers in many different areas, in ecology, in astronomy, in physics, even for some military purposes. There is really lots of those. So to finish this sort of crash course on the Takens theorem, let me give you some sort of illustration to have some picture in mind. So maybe the most canonical illustration for the Takens theorem is given by the Lorentz attractor. So what you see here is a Lorentz attractor. So this is a fractal attractor of a certain ODE in R3. The theorems are in discrete time. The picture is in continuous time. It's kind of easier to visualize maybe. Okay, so we have this attractor, and now if we pick a point on this attractor, then as time goes by, the point follows the flow on the attractor. And now each state of the system is described by three variables, x, y, and z, because we are in 3 dimensions. And now let's consider as an observable the projection onto the x-axis. Okay, so what you see on the right is a time series of the x variable alone of some initial point on this system. And now the question is how we can reconstruct or model the actual original dynamics just from this one-dimensional time series. Okay, and Takens theorem tells you what you have to do. You have to plot a new picture. This picture is done, let's say, in R3, whereas as the x-coordinate, you again put the original x-coordinate that you have access to. As the y-coordinate, you put the same x-coordinate, but just shift it in time. Okay, and as the z-coordinate, you shift once more by time. And now Takens theorem tells you that magic happens, and there should be a one-to-one correspondence between these two pictures. And in this sense, you can model the original, maybe unknown dynamics from one-dimensional time series. Now, of course, I'm not claiming that this particular observable is good because the theorem only says that the typical one, right? But this is the ideology. And the question is, how many delays do you need? Takens theorem tells you that k greater than twice the dimension of x will suffice, typically. Okay, so after this, I can tell you what our work and what this talk is going to be about. So we want to study embeddings with self-intersections. And by self-intersections, I just mean that phi is non-injective. Okay, so this means that as you embed your original phase space x by phi, well, some distinct parts of the space will intersect this, right? And the question is, can you still obtain some good or reasonable reconstruction properties even in the presence of self-intersections? Because maybe you want to draw your picture in smaller number of dimensions. Maybe you have hard time visualizing in R5, let's say. You want to see a model in fewer dimensions, or maybe you just don't have enough measurements to do whatever you need to do. And to deal with it, what we do is we take a probabilistic point of view. So we want to assume that apart from the system, we have a probability measure on the phase space X. And we want to ask whether maybe under weakened conditions, we can get an almost sure reconstruction. And by this, I just mean existence of a set of full measure on which the delay coordinate map is injected. This will mean that, okay, there are some intersections, but they are not too heavy from the point of view of this probability distribution that you are interested in. After removing a set of measure 0, you don't see intersections anymore. And our main result is that in this setting, the number of measurements can be reduced twice. So instead of embedding into twice the dimension of your set, it is enough to embed into something in the dimension strictly larger than the dimension of your set, and then you are no longer guaranteed to have true one-to-one correspondence between the system and the model, but at least it is one-to-one on a set of full measure. Now, another question that one might ask is, or maybe a problem that is often important from the point of view of applications, and sometimes is the main goal of this sort of analysis. Namely, maybe the properties of embedding are not good enough to have a faithful model of the unknown dynamics, but maybe at least we can use it to predict the future values of the observable, right? Because if the Takens theorem holds, this means that in this model that we built in RK, so for example, on this model in the picture, we have a well-defined deterministic dynamics. And what this dynamics does is it just takes a vector of k measurements to the shifted one, right? It just adds the next value of the observable. So if you have a good dynamical model, you can use it to try to predict future values of the observable. But actually for this, you don't really need to have an isomorphism between the original system and your model. It is enough to have a factor, right? Because then we still have a good, well-defined induced dynamics on the model, and we can use it for predicting future values of H. And this somehow hasn't been addressed previously from the, at least from the theoretical point of view. And now, what was actually maybe our main goal was to combine these two approaches in order to settle predictability conjectures of Schroer, Sauer, Ott and Yorke, who's in 1998 in Physical Review Letters stated some conjectures which predict that in a suitable sense, the number of measurements could be reduced twice in a probabilistic set. And we essentially can solve at least the main parts of the conjecture. And this also, all of this together, this also seems to provide a mathematical explanation of a certain phenomena that was observed numerically, namely, well, what we have in practice is this long time series of your observable. You don't know the original system. That's the whole problem. We want to reconstruct the original system. If you don't know the original system, you don't know what is the dimension. So you don't know how many time delay measurements you have to take in order for the Takens theorem to work. So what people did is they came up with sort of heuristic algorithms which try to maybe approximate and maybe not really the actual embedding dimension that the Takens theorem gives you, but something that will serve as an effective embedding dimension, something that gives you with good enough approximation, good properties of this prediction process. And what is interesting is that in numerical experiments for known systems, often this effective number of delay coordinates that you need turns out to be smaller than the one required by the Takens theorem, even though we know that the Takens theorem is optimal. You cannot go below twice the dimension. And I won't be getting much into this, or maybe not at all, except for now. If you look at these algorithms, you see that they indeed have a lot with common with this problem of the prediction of future values of the time series from probabilistic point of view. So it seems that at least on a heuristic level, we prove that you should actually expect to see a lower embedding dimension than what Takens theorem tells you, and this is what have been seen numerically. Okay, now this being said, I can start formulating some rigorous results. So I will state for you the sort of probabilistic Takens theorem that we have proved. I need to introduce some notions to do this. So first of all, we need a notion of dimension, and we work with measures, so we need a notion of dimension of measure. As you might know, there are plenty of notions of dimension of a measure. The one that turned out to be good for us is the so-called upper Hausdorff dimension, and this is just for a finite Borel probability, for a finite Borel measure mu on Rn. This is just infimum over Hausdorff dimensions of sets of full measure. Okay, a natural definition. There is also a famous diagram as measure one. Well, I don't assume that the measure is probability here. But if it is probability, then you ask whether it is. So no. You have to take it is infimum over dimensions of sets of measure one. No. Because you want to neglect something of measure zero and see what is the lowest dimension that you will see. So it's not equal to supremum over sets of dimensional sets of measure. Maybe if you haven't seen this before, it is useful to note that Hausdorff dimension of a measure can be strictly smaller than the Hausdorff dimension of its topological support. So it's not only important on what set the measure is distributed, but also how it is distributed there. Another notion that we need to introduce is a notion of typicality for the observables. And this is the so-called, we use following Sauer, Yorke, and Kazhagli in the setting, we use the notion of prevalence, which was already mentioned during Kuan's mini course. So this is supposed to be an analog of a set of full Lebesgue measure in infinite dimensional vector spaces. So if you are given a Banach space V, a set P is called prevalent if there exists a compactly supported Borel probability measure mu on V with the following property. So we want the set P to be large, to be almost full. And the definition is like this. What we do is we fix any arbitrary vector in V and we start perturbing it randomly. And by perturbing it randomly, I mean adding to W another vector E, which is chosen randomly according to nu. And now if for every V, we have that for almost every E, this sum is in P, this will mean that the set is large. It is prevalent. And this is actually, if V is Rn, this is equivalent to being a full Lebesgue measure. And here is the result. So we will work in the Lipschitz category. We assume X to be a compact subset of Rn, mu a Borel probability measure on X, and T, the dynamics, is supposed to be Lipschitz. And the main assumption is that K, this will be the number of measurements, is strictly greater than Hausdorff dimension of the measurement. There is no 2 here, and this is crucial, of course. And then the statement is like this, that for a prevalent Lipschitz observable, so for almost every, in this sense, Lipschitz observable, there exists a Borel set XH of full measure such that a nice thing happens. And now what is the nice thing? This depends on the assumptions. So if we want injectivity on a set of full measure, we still need to assume injectivity of T. And as I said in the introduction, there cannot be too many periodic points. And in our case, this means that the Hausdorff dimension of the measure mu restricted to the P periodic points, this dimension has to be at most P. For small periods, small meaning P between 1 and K minus 1. And under these assumptions, we have that for a typical, in the sense of prevalence, Lipschitz observable, there is a set of full measure on which this map is injected. This is the statement. So this is somehow a probabilistic Takens theorem. Now, the second part is when we do not assume T to be injective, and we do not assume any bound on the periodic points, and we are interested only in this prediction properties for the time series. Then we can claim that, again, for a typical observable, there is a set of full measure such that there is a what we call a prediction map S. This is map defined in the model, so in the image of this full measure set by phi, and it goes to phi of x. And now this map S, it satisfies that S on an observation vector is an observation vector of one step future of the point. So in dynamical terms, this just means that S is a factor of T, and the factor map is given by phi. Okay, and this means that at least there is, in the model, there is a set of full measure on which we have a well-defined dynamics, which we can iterate in order to predict future values of H. Yes.
H is...
Maybe this is a good thing to write down on the board. So phi th of x, this is a vector of length k of the values of the observable on the first k iterates of x.
Index K also.
Yes, there should be index k, but this would be too many indices. Yeah.
You don't see the measures in there?
In general, no, but if we go 2 steps further, if you want the set XH to be invariant, then you need to assume that the measure is invariant. And indeed, you want the set XH to be invariant if you want to be able to iterate the dynamics in the model, right? Because then this will be invariant under S as well. So yes, so you have to assume invariance if you want to have invariance of this. But in general, it is not used in a proof in any way, the invariance, other than saying if you have a set of full measure for an invariant measure, then you can find the set of an invariant set of full measure as well.
You choose every K bigger than dimension.
Yes. Yes. But of course, you want to choose as small K as possible.
Yeah.
Right? Every. Yes, absolutely. Absolutely. Yes. And the last statement, a natural question is what is the regularity of this map S, right? Because just having some maybe measurable map on some weird set of full measure, this doesn't give you any control on the prediction process if there are some errors in the measurements, right? So, well, in some sense, this is what these conjectures that I will talk about next are about, but somehow a basic result that we can get is at least continuity of F, continuity on this topologically maybe very weird set, which is an image of a set of full measure. But for this, we have to assume that K is greater than the Hausdorff dimension of the supported. Okay, just under this assumption, the statement is not true. So the map might not be even continuous. But if we have slightly stronger assumption, then we have continuity. And now, moreover, I stated all of this for Lipschitz in the class of Lipschitz observables, but it is actually true also in CK, for K from 1 up to infinity, including infinity. And the reason is that in the proof of prevalence, we have to construct this measure by which we do this random perturbations, right?
Measure has nothing to do with invariance.
No. I mean the measure from the definition of the prevalence. Yes, it is. It has nothing to do with the invariance, almost nothing to do with the system.
What does this depend on measure?
The choice. So,
Will you go back to the
yes.
System always said you can do it.
Yes, of course. The set that you obtain, it depends on the.
But then if you will okay, then you have a chance to.
If you are greater than twice the dimension, then you don't need to look for a set of full measure on which you have independence. Yes. So what I was trying to say here is that this measure from the definition of prevalence, which you have to construct to make random perturbations, it lives in the space of Lipschitz maps, but it actually lives in the finite dimensional subspace of polynomials of degree up to something. And as this is also included in all the CKs, actually the result is true in the sense of prevalence for all the spaces CK. So coming back for a moment to the example, you see the dimension of the Lorentz attractor is estimated to be somewhere between 2 and 2.5. Okay, so the classical Takens theorem would actually require 5 time delays, right? So this picture.
Maybe parameters.
Yes. Of course. This is one specific.
There is one classical parameter.
I guess that's the one. Takens theorem requires 5 dimensions, right? This picture should be 5-dimensional. So this is actually not a very good illustration for the original Takens theorem. But because this dimension is smaller than 3, it is actually rather an illustration for our theorem, right? So we actually cannot guarantee that there is a 1-to-1 correspondence, but typically there is almost surely 1-to-1 correspondence. And this is, as far as I know, this is a genuine picture. So indeed, at least heuristically, this picture doesn't seem to be very much folded with respect to this. But this is, of course, just handmade. Okay, so now let me go to these conjectures of Schroer, Sauer, Ott and Yorke. So as I said, this is again about predicting time series of the observable in the probabilistic setting. So once more, somehow the goal is to say how good can be the prediction process for predicting one-step future value of the observable from the previous ones. Okay. So in terms of this map, this is just predicting phi of tx from phi x, right? And the main part of the conjectures is to have some more or less explicit bounds on the prediction errors. So what these authors do, they introduce what they call prediction errors, which I will define for you in a moment, and state conjectures saying that if certain dimension of your measure is smaller than k, then you can say something about the decay of the prediction errors as you increase the accuracy with which you make measurements. This is somehow the idea. So now for simplicity, I will skip even more indices. So now phi of th is just phi. But of course, there is dependence on the dynamics and the observable. And so what I will do now is, in order to introduce this prediction errors, I will define actually a very silly random algorithm for predicting the future values, and then tell you how the prediction error is given in terms of this algorithm. This will be probably easier than just giving you the formula written. So we are given y. Y is a measurement vector in the model space. Okay, so this is phi of some x naught. And the goal is to predict the one-step future of y, which is phi of tx naught. Okay, and we do the following idealized algorithm. We think a new initial vector in the original system, randomly according to mu, but we only look at those x's for which the distance between the projection of x by phi is epsilon close to y. Okay, so we have, maybe I should draw some picture. So here is the original system. Here is maybe the models in k dimensions. Okay, here is the map phi, and now we have some measurement vector, some k-dimensional vector, right? And what we do is we pick a point randomly, but only from those points which project epsilon close to y. Okay, so in other words, what we do is we condition on the pre-image of an epsilon ball by phi, right? Sorry, so x is somewhere here. Here is x and here is phi of x. Okay, great. And now maybe x is far away from x naught. Y itself comes from some guy x naught. But maybe if there are the self-intersections in the embeddings, maybe they are far away. And now we approximate the future value of y as phi of tx. This is a random approximation of phi of tx naught. And the point is that, so this is some random variable, right? You choose x randomly conditioned on this, and you look at phi of tx. This is a random variable. It has some standard deviation. And now the smaller the standard deviation is for some fixed epsilon, the more unique is your prediction of one-step future value, right? So you want to know that for small epsilons, this is small. So this is the prediction error. If you prefer formula, here is a formula. So mu y epsilon is a conditional measure in the original system where you condition on being in the phi pre-image of epsilon ball around one, right? And this is just a standard deviation of phi of tx, where x is chosen according to mu y epsilon. And now a point y will be called predictable if the limit as epsilon goes to 0 of this prediction errors is 0. So this just means that if you can have arbitrary good approximation of y, then you will have essentially unique prediction of the future value of the observable. And so this is, as you see, this is a very silly algorithm. This is not something that you can do in practice, especially if you don't know the original system, and this is the whole point. But there are more realistic algorithms, which I don't want to go into. For example, the so-called Farmer-Sidorovich prediction algorithm, and actually this condition of predictability, it ensures convergence of this algorithm, which does the same thing, but just from a long sample, from a long time series for ergodic systems. So it may seem idealized, but it has something to do with something that actually people do in practice. And now, okay. To state the conjecture, so the conjectures are something about the speed of, or first convergence to 0 and then speed of convergence to 0 of these prediction errors, but they happen to be stated only for a very special class of dynamical systems and invariant measures for them. So, let me tell you what is this class. and then what is the notion of dimension which they use, because it's not the Hausdorff dimension, and this is somehow the trouble in the story. But let me tell you right away that these notions are not needed for our positive results. So our results are that the conjectures hold in much greater generality than whatever this class of measures is, and for a different portion of dimension. But for the negative, but we also have negative results that the original formulations do not hold. And for the negative results, you of course need to know what these notions are. So, what is a natural measure? We assume that the dynamics happens on a compact Riemannian manifold, that T, the dynamics, is a diffeomorphism, and that we have a compact attractor lambda. By a compact attractor, I just mean a compact invariant set with some open Bayesian of attraction, which I denote by B. This is the maximal Bayesian of attraction of lambda, which we assume to be open. And then measure mu is called a natural measure for this diffeomorphism if almost every initial point in this open Bayesian of attraction, almost every in the sense of the volume on your Riemannian manifold, equidistributes according to mu. Okay, so this is something similar maybe to a physical measure, but you want it to happen on the full, on the set of full measure, not on the set of positive measure. So, so these are very special measures. It's not every diffeomorphism of a compact Riemannian manifold even has such a measure. Okay, so this is, this is a quite a restrictive class, and the notion of dimension, which is used in the conjectures, is the so-called information dimension, or also known as the entropy dimension. So this is, I will define it, this is a notion of dimension based on entropy. So what you do is you denote by the M the partition of the Euclidean space into dyadic cubes of side length 2 to minus M, the most standard partition into cubes, and you define the information dimension as the limit as M goes to infinity of the Shannon entropy of the measure mu with respect to this partition normalized by F. Okay, here is the formula, if you prefer. And this is a nice notion of dimension. If you are of a measure, if you are in Rn, then this is between 0 and n, provided that the limit exists. Okay, the limit doesn't have to exist, and if it does not, then you consider upper and lower limits with these bars. So now we have everything to talk about these conjectures from '98. So there are two conjectures.
Could you show again?
Yes. Yes. So this is the entropy. Yes, exactly. So if you are, for example, I don't know, a Lebesgue measure on the unit cube in Rn, then this entropy will be maximal, and the maximal means m times n. Right. Okay.
Special thing, the capital N is lost.
Yes. The definition. Yes, of course. So yes. Maybe I assume here the measure to have compact support, because otherwise you could have a measure with infinite entropy in a given scale. And
the big measure. Yeah, okay.
So here are the conjectures. This is not the full statement, and the conjectures themselves, it's a physical literature, physical review letters. It's not stated very precisely, but quite precisely. So the conjecture is like this. Assume that you have a natural measure, and K, the number of measurements, is greater than the information dimension of the measurement. Okay? Then two things happen. First of all, for typical observable, almost every point is predictable. So if the number of measurements is large enough, then at almost every point you have this in the limit as the scale of your approximation error epsilon goes to 0, you have essentially a unique prediction of the future value. And a stronger conjecture 2, which is more quantitative, the following one. So in some sense, we want to say, okay, how fast, if we know that this error converges to zero, how fast does it happen? And this is stated in the following form. So what you do is you fix some delta. This is maybe your margin, and you want to say. So we know from point one that the measure of the points for which the prediction error is greater than delta, as epsilon goes to zero, converges to zero. And the question is how fast? Well, the authors predict this to decay as epsilon in the power k minus information dimension, which is positive if we make this assumption. Sigma is this prediction error. So this is the standard deviation of phi of tx, where x is chosen randomly on the with the conditional measure on the preimage of the. Okay, so you look at all the guys that map epsilon close to y under phi. You go one step future in your original system. You project down, and now you ask. We know that before the step they were epsilon close to another, but now maybe they start diverging a bit. The standard deviation tells you how much they diverge.
Right, maybe I'm confused a bit there. You are right in thinking that in general information dimension is sort of difficult to estimate. Just like so, the condition, if I must say, that your k, which you choose, should be bigger than no, somewhere. Yes, probably here. Yes, should be bigger than this is information dimension.
Yes.
Right. And information dimension probably defines by the same by generalization the same way like Hausdorff dimension of the matrix.
Not really, rather like box dimension, because
intersection being non-zero.
I mean, this is dimension of
Yeah, there is a measure of C.
yes, of course. Yes, so in some sense, yeah. I think that if this is something that you want to kind of approximate, I would expect it to be easier to approximate than Hausdorff dimension, because Hausdorff dimension is something kind of abstract, right? You have this Hausdorff measures, and then you look for the critical parameter. And here you just look at some fine enough partition for you. So when you have a measure on this partition, this is like a finite distribution, and you just calculate explicitly this formula. It's not boxed, but it's
measures of box.
Yes, of course. It's a lower bound for the base dimension.
Always greater or equal than the correlation dimension. Yeah, the last because you don't have measure equidistribution.
Exactly. Yes. So there are different ways with which you take the boxes. Okay, so this is the second conjecture. There are also some additional statements, but I don't want to get into it. And here are our results. So first of all, we can prove that both of these points are not true as they were stated. And the reason is we construct an explicit counterexample in this class of natural measures, which is some diffeomorphism of a three-dimensional manifold, for which this does not hold. And the reason is that the information dimension is not a good notion of dimension for this problem. That's somehow the observation. However, the first conjecture, so just the predictability thing, the convergence to zero, is true in much higher generality for general measures and Lipschitz maps, so exactly the same setting as this theorem that I was stating before, as soon as you replace the Hausdorff dimension with the information dimension with the Hausdorff dimension. So the Hausdorff dimension, in some sense, is the correct one. And actually, the statement that the conjecture one is true in this setting, this quite easily follows from this theorem that we had before. The consequence of this is that the conjecture is true as stated, conjecture one is true as stated for ergodic measures. Just because for ergodic measures, so in general, there is no comparison between information dimension and the Hausdorff dimension. You can have one very small and the other very big, or vice versa. But if your measure is ergodic, then the information dimension is an upper bound for the Hausdorff dimension. So then actually this condition implies that also the condition for the Hausdorff dimension holds, and we are back in the visits. So maybe the authors had ergodicity in mind, but they didn't say it. So this is why we are saying that the conjecture is not stated. And now the conjecture too. So the upper bound, so we already know that because the conjecture one does not hold in general for information dimension, we know that the second one is not true as well. But again, it is true. But what we have to do now is we have to replace the information dimension not with the Hausdorff dimension, this is not enough, but with the box counting dimension of the support. So unfortunately, we have to go to the notion of dimension, which depends on the measure only through the support. But this is somehow what we can get, and this is for the upper bound. So, okay, I will give you maybe a bit more precise statement in a moment. In general, this second conjecture is also not true for the Hausdorff dimension, unlike the first one. But here, the example which we have is not in the class of these natural measures. So we can do it we can cook up some general measures, but we don't quite know whether we can realize it as a natural measure. Okay, so I have a couple of minutes left. So maybe I will give you a little bit what we actually prove about this conjecture too. So as I said, this will be an upper bound. And now we have to change the information dimension to the upper box counting dimension of the support. And also we have to make some arbitrary small loss in the exponent here. So what we actually prove is that for every positive delta and every positive theta, for a prevalent observable and small enough epsilon, this inequality holds. Okay, so the bound is epsilon to power k minus the box counting dimension minus some theta, but you can make theta as small as you wish. But well, we don't know this. Maybe as theta goes to 0, then how small epsilon has to be? Maybe it diverges to 0. So maybe in the limit we don't have the bound. Actually, we prove something even a little bit stronger than this. We not only prove that the standard we not only prove that the measure of the points for which the standard deviation is large decays like this, but even the set of points for which there at all exists one point which before the iteration they had close measurements, but after the iteration they are delta apart. So even for this here is delta. No. So okay.
Then on the right hand side.
Okay. So there are two ways. Yes. So there are two ways to say it. I can either say that for fixed delta and theta, this holds for epsilon small enough, or I can say that for fixed delta and theta, this holds for all epsilons, but there is a constant here which depends on delta and theta. So this is the dependence on delta. Okay, so this is the statement. Now I have 5 minutes left, so I won't be talking about the proof. I can tell you very briefly something about this counterexample, maybe. Because the counterexample is not too difficult to come up with, it's maybe more difficult to prove that it is actually a good counterexample. So maybe instead of this question of predictability, let us focus on an easier question to give a counterexample to. Let's think about this injectivity on a set of full measures. Okay, and what I want to tell you is that the information dimension is not a good notion of dimension if you want to use it for a statement like there is a set of full measure on which you are injective, provided that k is greater than the information dimension. So the problem with the information dimension is that it is essentially an affine function of the measure. If I have two measures of some information dimension and I take their convex combination, then the information dimension of the convex combination is essentially a convex combination of the information dimensions, which means that, for example, a measure like this, I take half of the mass in something small, for example, in a point, and I take half of the mass in something larger, for example, a circle. Okay, so here I have 1/2 of the Lebesgue measure on the circle. Now, this is a measure which has information dimension equal to 1/2, and the Hausdorff dimension, well, the Hausdorff dimension picks up the larger part, right? So the Hausdorff dimension is equal to 1. And now, so let's take this example. The information dimension is 1/2, so we can take k equal to 1. But now you see the problem is that there is no Lipschitz map from the circle to the real line, which is injected on a set of full measure, of a full Lebesgue measure. This is something, so we know that the circle does not embed topologically into the real line, but it also does not embed in this measurable distance, okay, via a Lipschitz map. So this shows you that but you see, if now I take this convex combination, that I have something of dimension smaller than 1, but I still cannot embed this measure in a almost surely injective pattern into R, right, into one-dimensional space, just because the circle itself does not embed, right? So this shows you that the information dimension is not good notion of dimension, at least for this almost surely injective embeddings. And now what you have to do to disprove the conjecture is you have to put some dynamics on it, for example, an irrational rotation on the circle, and prove that it is the same intuition is true when you discuss this predictability. Okay, and then you have your example, and then you have to realize it as a natural measure, which is not terribly difficult, but is also not completely immediate. At least it was not for us. Okay, so I will finish here. Thank you very much. Yes.
Has something been done for, if you imagine, so if this is supposed to be used in applications, you could imagine that the underlying dynamical system is slowly varying with time?
Yes. You mean like a non-autonomous dynamics?
Yes. You could imagine that there's a parameterized dynamical system behind it, and the parameter is very slowly changing with the number of iterates. So you want to weight the more recent iterates more heavily, the more recent observations more heavily.
Right. So I don't think that anything was done in like this particular setting that you are talking about, but there are results for sort of a non-autonomous dynamics. Then somehow they are still generic in the space of dynamics, so they are not really for a fixed dynamics. So there are kind of a non-autonomous analogs of this original result of Takens, which was for the generic dynamics. I'm not sure if this answers the question, but this sort of things were done. The point is that the proofs of this sort of result, the dynamical part of it is not too heavy. The dynamics come in by some finite number of iterates, combinatorics, and so on. So my expectation is that you can play quite some games with what you mean by the dynamics in this context. So maybe this is the way I can try to answer.
No, but if we need autonomous, but parameter changes of dynamics. And then it looks like stability Kupka-Smale phenomenon. So some individual periodic points may change character, but good even for finite number of parameters.
This parameter could be also considered as part of the dynamic.
Yeah.
About the limits system which didn't yet approach this parameter is still varying.
You need typical properties even for maps parameters. It makes sense. I mean, Kupkas may accept some individual.
Look at the delayed time series, but not with delays T50,
Yes.
but with general delays T1, T2, T3. You would without survive.
So I think they should. You have to think what is the proper assumption about the periodic points and stuff like this. But I think they should. So, for example, there are results not for general delays, but if you have if you still have a discrete time iteration, right? And you can do stuff like, for example, okay, if you mean a discrete time iteration, not necessarily a continuous time, then there are results which tell you that if you look at window of length n and out of it you pick arbitrary k iterates, then there are results. We haven't proved ones like this in this probabilistic setting of ours, but I think for the original Tackless theorem there are results. But now, if you are in a continuous time dynamics and you do, I don't know, some irrational differences between the steps and so on, then I don't know. But again, coming back to the previous answer, this is somehow not heavy dynamic. The proofs are not heavy dynamic. The dynamics come in through the combinatorics of finite orbits. And then you have to, if you are in a more general situation, you kind of have to be able to replay this game. And in some situations you.
So let's try this.